Alright, so number 20. Let's get going. So on this problem here, we have a cliff and we launch something actually at 30 degrees below the horizontal. Like this. So we want to know how long it takes to reach the ground 200 meters below. So this is 0 and we actually start off at a y naught of 200. So first of all, let's get v naught in the y direction. That's going to be 700 times the sine of 30. And that gives us 350 meters per second. Now, since this is downwards, I'm going to put negative 350 in front of it because it's in the same direction as gravity. So let's set up our equation. We have y equals negative 1/2 gt squared plus v naught y t plus y naught. So we have 0 equals negative 4.9 times t squared plus negative 350 times t plus 200. Now we use quadratic formula, so t equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And so when we go ahead and solve this, we're going to get a time equal to, of course, 0.57 seconds. There's a negative answer that we get, of course, but we throw that out because it's just a nonsensical answer. Now, number 21, we have a diver jumping off a cliff in Hawaii, blah, blah, blah. There's an outcrop in the rocks, so she has to clear these rocks that are 7 meters out of the base, and she's on a cliff 45 meters high. So let's just go ahead and take a look at this and jump in. That was fine because it's diving. Alright, good. So this is 45 and this is 7. And let's be clear, whenever we see something like this, let's be clear. Y naught is 45, y is 0, x naught is 0, x is 7. So first let's get the time to fall. So we have y equals 1/2 negative 1/2 gt squared plus v naught yt plus y naught. So that's going to end up being 0 equals negative 4.9 t squared plus 0, because v naught in the y direction is 0, plus 45. So t is going to be about 3 seconds. So what we need to do is we need to clear 7 meters in 3 seconds. So there's a lot of ways we could get this. Let's just use the standard formula x equals v naught xt plus x naught. So that's going to be 7 equals v naught x times 3 plus 0. So v naught x is going to be 7/3, which ends up being 2.33 meters per second. So that's it for that one. There we go. There we go. This is a good one. So if a person can jump 1 meter high on Earth, how high can they jump on the moon? So let's just see. Lots of ways to do this one. So let's just get the time. Let's just see. So a person can jump 1 meter high on Earth, how high can they jump on the moon? So let's find the speed that they jump at on Earth. So let's just kind of jump in. So vy squared equals v naught y squared plus 2gy minus y naught. So we have 0 at the top of the jump equals v naught squared plus 2 times negative 9.8 times 1. So we're going to end up getting v naught squared equals 19.6. So v naught ends up being, when we actually calculate this, square root of 19.6. It's about 4.43 meters per second. Now, let's figure out how high they jump on the moon. So we have 4.43 squared. So 0 squared, that's the height, the speed at your highest point, equals 4.43 squared plus 2 times 9.8 over 6 minus y minus 0 minus 0. So we then get, so we square this, we get negative 19.6 equals 9.8 divided by 3 times y. And so we get 3 times 19.6 divided by negative 19.8. And that'll be the height that we get. So let's go ahead and calculate that. So 19.6 times 3 divided by 9.8. That's going to give us about 6 meters. Wow, that's pretty cool. So there we go. Now, let's move on to question 23. This is very good. So now we got James Bond and a Corvette. I'm trying to get all this. I like this. This is a good problem. So why don't we go ahead and actually snip this picture out and use it in the problem. So we'll go ahead and get that. Nice. All right. So let's turn the page here. Oops. We'll go here. Get a new page in the old notebook. And put this in there. Nice. It's nice and big. So this is a good little picture here. So let's just zoom in a little bit. So we can get this whole picture here. Good deal. Now let's back up to the problem. The problem says we're trying to jump into a speeding Corvette to capture the bad guy. So we get all this great stuff labeled. Wow. So how long must James Bond wait to jump in order to safely make it into the car? This is just a really tough problem. Wow, I like this one. In fact, let me just zoom this up here and see what's going on. So first, let's get some equations down. So for the car, we have, for the car, so if I have a purple color, it'd be great. Wouldn't it? Purple, oh, look at this. Purple equation for a purple car. So x car equals V naught car T plus 440 meters ahead of the helicopter. Wow, that's exciting. And then here, wow. And then, so there's going to be that. And then the helicopter is moving at 100 meters per second. So let's just do the x equation for the helicopter. Just pick a nice, I'll pick blue. So we have x of the helicopter equals 100t. This is great. And James Bond's going to try to somehow dive into this helicopter. Now, let's figure out how long it's going to take James Bond to fall. So we have y equals 1/2 gt squared plus v naught yt plus y naught. Okay. So here we know that v naught y is 0 and y naught's 120. So we can actually get negative 120 equals negative 4.9 times t squared. We solve for t, so let's go ahead and get t. So that's 120 divided by 4.9. We'll get the square root of that. So wow, if he's going to fall 120 meters, looks like it's going to take him 4.95 seconds to fall. That's great. So now let's figure out how long it takes the helicopter to catch up to the car. So we've got 100t equals, oh, this is 30 meters per second. So that's 30t plus 440. So we got 70t equals 440. So how long does it take the helicopter to catch up to the car? That time is going to be 440 divided by 70. Wow, so we got 6.28 seconds for the helicopter to catch the car. So if it takes James Bond 4.95 seconds to fall and it takes him 6.28 seconds for the helicopter to catch the car, the time to wait is going to end up being 6.28 minus 4.95 seconds. So 6.28 minus 4.95 gives us 1.33 seconds. Wow, that was a good one. I like that one. Pretty tricky. Good stuff. Yeah. Let's see. Wow. So here we go. So 24 and 25. You know, there's just a part of me that thinks I want to leave two problems on here kind of undone. So I'm going to actually leave 24 and 25 on here undone because I have a couple people that I told them that their condition for retaking the exam was that they needed to do everything in the learning packet. I don't just want them copying my solutions. I want them actually working. So they're going to have to do a little legwork around these problems, and so are the rest of you. So I want to make sure that you guys are actually doing the work that's required of you. So 24 and 25 are going to be challenge problems that if you can get these done without my help, that'll be a really good way to ensure that you guys are really doing the legwork here to get things going. So good luck, have fun, and that's the end of the learning packet. By the way, these are way harder than what you'd see on the exam anyway, so if you can't get them, don't feel too bad about it. All right. Let me see. Actually, 25 you could do. Why don't we actually try that one? This is actually a pretty easy one. So hopefully you can get that. Let's see. We get 43. Let's just try it. So we got 39 meters is x, and we're going to hang time at 3.9 seconds. I'm going to calculate the angle which the ball is kicked. So we're going to assume that it does this. So let's see what we can get here. So the hang time equals, so that's going to be V naught sine of, so 2 V naught sine of theta over G. So we want to get, interesting. This actually, so T is V naught sine theta. And let's also get X. So X is going to end up being V naught squared sine of 2 theta divided by G. It's very good. So we have these wonderful things. So what we could do is we could actually end up dividing quite a bit here just to kind of see. So if we got X over T, that would be V in the X direction. Interesting. So X over T is going to end up being V naught squared. Wow, this is actually a good problem. So I may do this in another video, I may not, but there's a lot to think about here. So we'll see what you can do with it on your own. It's good.